So this chapter is on temperature and heat, and we'll start with temperature. You're probably familiar with the temperature scale, so if I give you and I give you the Celsius scale and the Fahrenheit scale, and maybe the Kelvin scale. So this is 0, this is 32, and this is like 273. I think it's 0.15, but it doesn't matter. This is, of course, at atmospheric pressure. And then for boiling, it's 100 degrees. I suppose it should be 0 degrees, 212 degrees, and this is 373. Notice that the Kelvin scale and the Celsius scale are scaled the same. That is to say, a Kelvin and a Celsius degree are the same. There's 100 between boiling water and freezing water in both cases. And so we can write these things a few ways. We can say, like, the temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32 degrees. We can say, if we reverse that, we can say the temperature in Celsius is equal to the temperature in Fahrenheit minus 32 degrees times 5/9. This is just an algebraic rearrangement of that one. And then we can say the temperature in Kelvin is equal to the temperature in Celsius plus 273. And if you need to go from Fahrenheit to Celsius, to Kelvin, you can rearrange those and do that. And so I can just do an example. If for 100 degrees Celsius to temperature in Fahrenheit, I would say temperature in Fahrenheit, the temperature in Fahrenheit is equal to 9/5 times 100 degrees plus 32 degrees, which is equal to 180 degrees plus 32 degrees, which is equal to 212 degrees. So that's the Fahrenheit temperature that corresponds to 100 degrees Celsius. So you can do as many of those as you want for practice. So let's talk about thermal expansion. So if you take an object and heat it, these are little flames, right? It expands. It can be a piece of wood or a piece of metal or something like that. The reason it expands because when atoms gain thermal energy, they vibrate more, and that causes the object to expand. And so it turns out that the rate of expansion the expansion with respect to temperature, the change in length I would write it this way, is proportional to the length. This is dl dt is the change in length with respect to a change in temperature is proportional to how long it is. Hopefully this makes common sense, sort of. How much expansion you get depends on how long the object. An object that's really short isn't going to have much expansion. An object that's really long is going to have more expansion. And so, assuming they're made out of the same material. And so, you can always change a proportionality into an equal sign by just inserting a constant. So we write it this way. The change in length of an object with respect to a temperature is equal to alpha. So that's a proportional sign for math, and that's a Greek letter alpha. Don't get those mixed up. L. And so this is the proportionality relationship. This is the relationship between the change in length with respect to temperature is proportional to the length, right, to how long the object was in the first place. And so alpha is called the coefficient of thermal expansion. So let me just give you an example. For the Golden Gate Bridge, it's 2 words. The length is 1,275 meters. Between winter and summer, temperature change is delta T equals 55 degrees Celsius. In other words, T winter is like minus 15 degrees, and T summer is equal to 40 degrees. And so we want to know the length change, right? And so we had dl dt is equal to alpha L. And so that says that dl is equal to alpha L dt. And so we can approximate this and just call this the change in length. The dl is equal to alpha L times the change in temperature. And we know all these if we assume that the bridge is made of steel. So alpha for steel is 12 times 10 to the minus 6th per degree Celsius. Can you see that on there? Right. And so that means the length change is equal to 12 times 10 to the minus 6th per degree C times 1,275 meters times 55 degrees C. And so that comes out to 0.84 meters. That's actually a long bit. That's bigger than this, right? And that expansion has to take place in the bridge. Now the bridge probably has sections that are shorter than 1275, but a lot of expansion has to take place between the winter and the summer on the spans in the bridge, and the bridge has to be designed to account for that, to allow for that. Often, even on overpasses, you'll see things that look like this, like intertwining fingers on the road between the winter and the summer. In the winter they look like this, and in the summer they look like this, to allow the span of the bridge to expand into the supports. Okay. So let's talk about thermal expansion, how it affects area and volume. We already did linear expansion. We said, look, delta L is equal to alpha L delta T, where delta L is the change in length, alpha is the coefficient of linear expansion, L is the length of the object, and delta T is the change in temperature. Well, now we want to know, how is delta A related to A, right? The change in area related to the area. And so if you look at an object, I'll draw it like this, right? And say it expands when its temperature is changed, right? Like this somehow. That's probably not a very good drawing. But I can say, look, this is one dimension, this is L1, and this is L2, and this is delta L2, and this is delta L1, right? And so this area, this is area, and this is the change in the area, right? What it expanded into. And so we want to know how these two are related. Well, we already know that delta L1 is equal to alpha L1 delta t, because that's just the coefficient of linear expansion here. Similarly, delta L2 is equal to alpha L2 delta t. And so we can calculate, say, this area right here, right? Its length is L2, and its width is delta L1. And so I'll call this, what will I call this? I'll call this like B1. B1 is equal to L2 times delta L1 is equal to L2 times alpha L1 delta t, which is equal to alpha times A times delta t, because L1 times L2 is just the area, right? This is B1. I'm going to call this B2. B2 is equal to L1, because that's the length this way, L1 times delta L2, right? That's the area of this piece. And we're going to say this is equal to L1 times alpha L2 delta t, because delta L2 is alpha L2 delta t. Let me straighten that up. Right? And so that's equal to alpha times the area times delta t. Right? And so these two guys end up with equal areas, right? B2. And so the total change in area, if I neglect this piece, which is just a tiny expansion this way plus a tiny expansion this way, multiplied together. And so I'm going to assume that's small relative to these two, relative to the two strips. I can say delta A is equal to B1 plus B2. That's equal to alpha A delta t plus alpha A delta t is equal to 2 alpha A delta t. And so this is the coefficient of thermal expansion. This is the equation for linear expansion, for area expansion, sorry. This is equation for area expansion. Instead of having an alpha, I just have a 2 alpha, where alpha is the coefficient of linear expansion. And you can show that the same thing is true for volume. It's equal to 3 alpha volume delta t. And so if I have like a gas can, its change in volume for a given temperature change is just 3 times the coefficient of linear expansion times the volume times the temperature change. The area is 2. Sometimes you'll see this piece referred to as beta, 3 times alpha, and then you'll see delta V is equal to beta V delta T, and they call this thing the coefficient of volume expansion, but it's just 3 times the coefficient of linear expansion. So suppose your 60-liter steel gas tank is full and at 15 degrees C from cool gas kept underground. All right, how much gas spills out when it warms to 30 degrees? So you put gas in your tank, and now it's the gas and the tank are at 15 degrees Celsius. But in the air outside, it warms up to 35 due to the engine and other stuff. And so when that happens, both the gasoline and the tank expand. And so we want to know the difference between those two numbers, right? And so we can say, look, delta V for the tank is equal to 3 alpha V tank delta T. And then similarly, delta V for gas is equal to 3. So I'll call this, since it's steel, I'll call that alpha S, 3 alpha gas. The 3 alpha gas is the number that I put in the table a minute ago. And you don't have to multiply it by 3 because I already gave it the 3 in there, but we'll put that number in a second. V gas, delta T. The delta T's are the same, right? Because they both go from delta T equals 35 minus 15, which is 20. Right? And so the volume of the spill is delta V gas minus delta V tank, which is 3 alpha G, I'd write it that way, times V gas times delta T, minus 3 alpha steel V tank delta T. So these two guys are the same, right? They're both 60 liters. It's the alphas that are different. And so this really comes out to the V spill is equal to 3 alpha for gasoline minus 3 alpha for steel, V times delta T, where I can use either V gas or V tank because they're both 60 gallons, so I'll just call it V. Right? And so this is 950 times 10 to the minus 6 per degree C, minus 3 times 12 times 10 to the minus 6 per degree C, times 60 liters times 20 degrees C. When I evaluate that, I get about 1.1 liters. So if you fill your tank up to the very top when it's cold, as it warms up, it's going to leak out gas. Unless you're driving fast enough to burn that off before it warms up.